Hey guys, welcome to this video on orbital motion. This is a continuation from part 3 of where the last videos you turned in are. And yeah, I'm hoping to continue this to for 3 more parts, and then we can hit 1 more on rotational motion, and that'll be it for the semester. So there are going to be 4 more videos after this. Anyway, let's get into orbital motion, yeah? So we've discussed 2 ways to analyze trajectories of objects, yeah? And these ways have been, projectile motion, as well as orbital motion. All right? Now, what's the difference between projectile motion and orbital motion? Well, number one is the trajectories. In projectile motion, as we've learned in class, we're dealing with more parabolic trajectories. If an object is here, and this is my ground, and this is a cliff, and an object would just be going from that cliff down in a parabola. This is my ground. But in orbital motion, we have a circular trajectory, right? Yeah. But the biggest difference, all right, is the launch velocity. All right, this is just the same as the regular velocity, but yeah, it's just the same as the regular velocity, and you could define it as the velocity an object is launched at. All right. So the biggest difference with in orbital motion and projectile motion is the initial velocity an object experiences. All right. Orbital motion requires a large velocity. All right. Yeah. So yeah, just quickly recapping projectile motion trajectories, parabolas. If I have an animal or the penguin, it's from a cliff to the water, it's a parabola. Or if I have a cannon, I shoot it, it goes up and then back down. The reason the object falls down to the ground is because of the velocity it's launched at. It's not launched at a fast enough velocity to pick up. It's not launched at a fast enough velocity to pick up orbital motion. And mathematically, these trajectories can be described by parabola. Yeah. So now let's discuss orbital motion. Let's actually discuss it now. So the first thing we need to know is we are traveling around a planet. All right, a planetary body per se. Orbital motion is done around large planetary bodies. So here, I tell you, an object is launched at a fast enough velocity, so it goes into orbital motion. Something we've discussed already today. So because gravity is the only force acting on an object in both orbital and projectile motion, the objects are both in free fall. All right? So when we're dealing with orbital or projectile motion problems, you have to realize this: we're analyzing free fall acceleration. Like the objects are in free fall. So that means the only force on those objects is the weight force. All right. So I know we've talked about how velocity is the main reason that we experience orbital motion. However, velocity is not the main reason. It's not the only reason, sorry. So a planet such as the Earth is in a gravitational field. All right, the Earth is in the gravitational field. So it pulls objects to its center. All right. So if we launch an object at a small horizontal velocity, like so here I'm referring to projectile motion. So if we launch an object at a small horizontal velocity, yeah, gravity will pull it down faster. Sorry, gravity will pull it down to the center of the Earth before it goes very far. All right. So think about the strength of not really the strength, so to say, but what's going on is that because we're already so close to the Earth, we feel a gravitational force pulling us to the ground so much that there's no way we can actually break from it, so to say. All right. But if we launch an object at a fast horizontal velocity, yeah, gravity will still pull down the object towards its center. Let me just get, sorry, I just need more space to write. But because the Earth is spherical, what's actually going on is that the object keeps missing the ground. All right? So, think about it this way. If I throw a ball, yeah? And if I launch a ball actually, I'm going to have my gravitational force pulling this down until I'm back to the ground. All right, imagine this projectile motion and my ground is here. And yeah, I'm going to have gravity pulling this down constantly. Yeah? But in orbital motion, what goes on is that, yes, it's going to be pulled down, but it will miss the ground. It won't reach the ground. Instead, the object will keep going in a circular motion. And gravity is going to keep trying to push it towards the center of the Earth, but it will never get there because we have a high enough velocity. All right. So all these here are G vectors. All right. This is the force here is G. Or if you like the weight, you can put the weight vector is applicable. So yeah, that's basically what's going on. All right. That's the main reasoning behind why we experience orbital motion and experience projectile motion as well. It's because of in both of them, the force of gravity is still present, but in orbital motion, because we're moving so fast, we keep missing the ground. We keep missing the ground a little bit and just following the Earth's curve. I hope that's something you can imagine. All right. So what we've learned so far is gravity is basically responsible for an object moving in a circular path when it's undergoing circular motion, undergoing orbital motion. All right? Gravity is responsible. So basically, in our analysis of circular motion, it's safe to say gravity is responsible for the centripetal acceleration causing objects to move in a circle. Like we saw here, yeah? The reason why we're moving in the circle is because gravity is just keeps drawing us to the center, but the Earth is spherical, so we keep missing the Earth, and that because we keep missing the Earth, we're going in a circle, and just in that space of never reaching the Earth but never leaving it too. So we're forming a circle. So now, what we've basically said here is that an object in orbital motion is experiencing uniform circular motion. Yeah. And so here the question here is, how do we find orbital speed of an object? How do we find the orbital speed an object would need to go around the planet? Well, let me draw it. It's actually a lot easier than we might think. I've actually already done this for you in class, but so I hope this rings a bell. So this is my planet, and this is my object in undergoing orbital motion. Yeah, I'm going around the whole planet. How do I find the speed? Well, I know that I'm in free fall, so my only force is weight, right? And remember, we're in the x direction, so f of x is going to be equal to weight, and I can apply Newton's 2 now. Apply Newton 2. I'm going to get MAC is going to be equal to, what's the magnitude of weight? mg, right? The m's cancel. AC is equal to G. What's AC equal to? AC is equal to V squared over R. I can plug in that. V squared over R. V squared over R. And equal to G. So I can cross multiply. And I see that V squared is going to be equal to RG. I can square root both sides. V is equal to square root of RG. Awesome. So that's basically what we have here now is the formula for finding the orbital speed. All right, the speed an object would need to arrive at orbital motion. All right, this is an important derivation. You should know it, but it's also worthwhile just knowing the formula, saying, okay, to find orbital speed, I have to square root the radius times gravity. So I have a summary of the lesson here. Feel free to pause the video and just write these. I think it's really important that you know these summaries. I'm going to read them very quick. Actually, I won't read them just to save you time on this video. So I advise you pause, you read them, they summarize the video. And I'll just reiterate about this formula here. Yes, it's good to know how to derive it, but it's also good to know that this is the formula for orbital velocity. All right, so G is our free fall acceleration, and R is the radius of the planetary body our object will spin around. All right, I hope you enjoyed that, and have a good day.